Bismillahirrahmanirrahim. In the last video, we have discussed about the torque speed characteristics of the induction motor. In this, we are going to see that how we can determine the different parameters which are required to develop your equivalent circuit for the induction motor and then are used to sketch the torque speed curves. Due to similarity between induction motor equivalent circuit and the transformer equivalent circuit, same tests are used to determine the values of the motor parameters. The tests which are used for the transformer equivalent circuit. What are those tests? First one is the no load test and the second one is the short circuit test. So in the case of induction motor, we use the same two tests, the no load test, and along with that we use the block rotor test to determine the motor parameters. And the DC test is also used to determine the winding resistance. So three tests are performed for the determination of the induction motor parameter. The first one is the DC test, and with the help of this we determine the rotor resistance R1, and then we perform the no load test. No load test means you are going to run your machine at the rated voltage. You are supplying the rated voltage to your machine and there is no load connected with that one. At that instant of time, all the power which is being absorbed by machine is basically going towards the losses. What are those losses? Rotational losses, right? Magnetization current. So it is just similar to the no load test in the case of the transformer. So you have the magnetization losses in the no load test and the rotational losses. So you can determine those with the help of the no load test. And the third test that is performed, that is the locked rotor test. It determines the rotor and the stator impedances. That is R1 plus JX1 can be determined, and the second one is the same for the rotor, R2 plus JX2. The rotor parameters, those can be determined, right? So now let's see that how we can apply these tests. So starting from the DC test. In the DC test, the purpose of the DC test is to determine the stator resistance R1. So a variable DC voltage source is connected between two stator terminals, right? And the DC source is adjusted to provide approximately the rated stator current. And the resistance between the two stator leads is determined from the voltmeter and the ammeter readings. So here you can see the two windings which are there between. Let's suppose this is the terminal A, this is the terminal B, and this is the terminal C, three phase terminals of your machine, and this is the neutral point that is inside your machine. It is not available at the output, may or may not be. So if we connect a DC voltage source over here, and this is the resistance to control the current in these windings, and what we are going to do, we are going to adjust the rated current in this winding, and that we are going to measure with the help of this ammeter. So measuring this current and looking at the voltage at the machine terminals, and we will be changing either this DC voltage source or this current limiting resistance to adjust the current in the winding. So usually we use the variable DC voltage over here, and we adjust the voltage in such a way that the rated current flows through this winding, and then with the help of that we can find out the resistance. Resistance is simply equal to V by I. Voltage divided by current, you will get the resistance because it is a DC voltage that you are going to apply, so simply you can use the Ohm's law. Okay, so RDC will be equal to VDC and the IDC, where IDC is the rated current of your stator winding that you have established. And in this circuit, if you observe, you have the two windings, so the resistance of one particular winding can be calculated with the help of this expression, that is simply dividing it by 2. So if you divide that resistance by 2, you will get the resistance of one winding, right? Okay, and if the stator is the delta connected one, then the per phase stator resistance can be determined with the help of this expression, that RDC into 3 by 2, you will get the resistance of the stator winding, per phase resistance. Okay, now the second test is the no load test. In the no load test, what we are going to do, we are going to run our machine at the rated speed by applying the voltage. So we are going to connect a voltage source over here, voltage source in this phase, voltage source in the second phase, and the third phase. Let's suppose that all the source is Y connected. So you have applied this voltage and you have adjusted it to the rated value. and the motor is allowed to spin freely. No load is connected, no mechanical load is connected with the shaft of your machine. The only load on the motor is the friction and the windage loss. So all power that is converted into the mechanical form is consumed by the mechanical losses. Because there is no output. So where that mechanical power is going? Why you are taking the input power? You are taking the input power to overcome the friction and the windage losses and the mechanical losses of your machine. So here you can see the power meters. 2 watt meters are being used. You are measuring the currents of all of these phases, and you are measuring the line voltage between line A and line B. Okay, so as you are running your machine at the no load, so the slip will be very small, because we know that the induction motor is usually operates in 1 to 10% slip even at the full load. So at no load the slip is just 1 to 2 or 3, maximum 3%. So your slip will be very small, your speed will be very close to the synchronous speed of the machine. Okay, so now if I look at the equivalent circuit and the no load situation, so over here you can see um, this is the stator side, stator resistance R1 plus JX1, and we have this magnetization branch if we consider the equivalent circuit, and this one is the rotor side. So now as this slip is very small, we can say it is approaching to 0. It's not exactly 0, approaching to 0. So when it is approaching to 0, so what about the power that is converted into the mechanical form? This R2 will be infinite, or we can say this R converted, that is this one, it is approaching to infinity as slip is approaching to 0. So because of that this resistance will be approaching to infinity, and because of that, what about the current in this branch? The current in this branch will be approaching to 0. So we are assuming that this I2 is nearly 0, no current in the rotor circuit. And why? Because the slip is very small, and as the slip is very small, then this is quite large as compared to your R2, and this R2 into 1 minus S by S is also very large as compared to your X2, right? So you can even ignore these ones. This one and this one can be ignored in front of this one at this particular condition. So if that is ignored, so you can draw your equivalent circuit like that, you have only this resistance, and definitely you have no connected load. So it means all of this mechanical power is basically the frictional and the windage loss. So this resistance is now representing the frictional and the windage loss, and that will be in parallel with your magnetization branch RC and GXM, right? So we can draw our circuit like that, and now we can combine RC and RF and RF and windage resistance. So the net combination is shown over here. That is the parallel combination of RC and this resistance, right? So we can represent our circuit like that. Why we are combining the RC is also usually very high, and the current in the RC is basically the eddy current loss, and that should be as small as possible. So RC is very high in practice. Okay, so we have now the second, we have the JXM, and the frictional windage and the core losses are combined together all over here. And what is the relationship between this and JXM? Losses are just a few percent of your total power, and these resistances are representing the losses. Those should be very high so that the current in these branches are very small. So this resistance is quite high as compared to your this magnetization branch reactance GXM. So what will be their parallel combination? You have very high resistance in parallel with the GXM, so you can even ignore this part, and you can say at this point you have only this part of the circuit that is available, right? So you can make an approximation, and it means if you can neglect that one, the whole of the current that is there at the stator is going to pass in this loop, and from there you can look at the estimation of xm, right? So from no load test, you are going to measure the input power with the help of the meters, and which is equal to the losses in your motor. The rotor copper loss is negligible. Why? Why it is negligible? Because R2 by S is quite high. This is quite high, and because of that the current is 0, so there is no loss. So P rotor copper loss is approaching to 0. So we are going to assume that over here that it is negligible, because I2 is extremely small and R2 into 1 minus S by S is very large. That is the resistance representing the power that is converted into the mechanical form. As the rotor copper loss is not there, so the input is basically equal to the stator copper loss, core losses, and the frictional and the windage loss. And the stator copper loss is 3 into I1 square into R1. So combining all of them together, we are going to call them the rotational losses. So input power is equal to the stator copper loss and the rotational loss. So rotational loss is given by this expression. Okay, now from the no load test, you can find out the equivalent impedance, that is x1 plus xm basically. Because if I go back and look at the circuit over here, uh, you can find the impedance by taking the ratio of the voltage and the current that is going to flow in this circuit. Let's suppose that is I, and we have assumed that this resistance is quite large, and the parallel combination of this one is nearly equal to simple jxm. So we are going to assume that only one resistance is there, reactance is there, jxm. R1 is usually very small as compared to this xm and x1. So impedance is usually, the impedance in this particular case will be giving you the sum of this jx1 and jxm. R1 we have already calculated with the help of the DC resistance test. So now we are looking forward for the x1 and gxm only. So the impedance that is calculated from the no load test, V phase, and the no load current, that is nearly equal to x1 plus xm. R1 is usually very small because it is representing the resistance of the copper winding. So if somehow you can find out x1 in this, so you can estimate xm, the magnetizing reactance of your machine. Now let's talk about the blocked rotor test. This is the test in which you are going to block your rotor. Your rotor is locked, it is not rotating, it cannot move. And you are going to apply the reduced voltage at the machine terminals such that the current in your machine is the rated one. So the rotor is blocked so that it cannot move. A voltage is applied to the motor, and the resulting voltage, current, and the power are measured when the rated current is going to flow in the stator winding. You observe the ammeter on the input side. And if rated current, because the maximum current, at maximum current you will be having the maximum losses in your machine, maybe, because at that point what is the stator current? I1, and what's the power? 3I1 square into R1, and that will be the rated loss because you have the rated current in your machine. So if you adjust the rated current by blocking your machine, by having the rotor jam condition, and you adjust the voltage and you have the rated current, you can find out the maximum losses. Okay, at the blocked rotor state, your machine is not moving. So what about your slip? Slip is equal to ns minus nr by ns. So nr is 0, so slip is equal to 1. If the slip is equal to 1, from the equivalent circuit of the motor, this R2 by S will be equal to R2. Or we can say that if you represent this R2 by S like that it has two parts, R2 plus R2 into 1 minus S over S. So only R2 is there. There is no power that is converted into the mechanical form because this S is equal to 1. This resistance goes to 0. It means no power is converted into the mechanical form. Only you have the rotor copper losses. Your shaft is not rotating. So that you can see in this circuit that this R2 by S is equal to R2. Okay, so net resistance impedance will be R2 plus JX2. And your magnetizing reactance that is in parallel to this one is quite high as compared to that one, because it is representing the flux linkage and all of the powers associated with those. So Xm is quite large as compared to R2 plus Gx2, and Rc is quite large as compared to R2 plus Gx2. So we can neglect Rc and Xm. So this branch can be neglected, and we say the whole of the power is basically flowing toward this part of the circuit, and in that we have R2 and Gx2, and this is passing through the stator. So the effective circuit is this one. The current is going to flow in this path. So now the current is passing through the rotor and the stator impedance. R2 plus Gx2 is the rotor impedance and the R1 plus Gx1 is the stator impedance. So you can estimate those two impedances with the help of the voltage and the current that you are observing at the voltmeter and ammeter. Voltmeter for voltage and ammeter for the current. Okay, so the AC voltage applied to the stator is adjusted so that the current flow is approximately the full load current or the rated current of your machine, and then the lock rotor power factor can be determined using the simple expression of the power P in, that will be equal to under root 3 times V line I line cos phi, or in terms of phase voltages you can write under root 3 into V phase into I phase into cos phi. You can determine it in either way. So you can determine the power factor, and the magnitude of the total impedance can be determined V phase divided by the current, right? So this is the locked rotor resistance. LR is indicating the locked rotor resistance. So blocked rotor resistance gives you this impedance, that is having the locked rotor resistance and the locked rotor reactance, and you know the power factor. You have calculated the power factor at no load. So then with the help of that one you can find out the resistance and the reactance, because the resistance is equal to impedance into cos of theta and the reactance is equal to impedance into sin of theta, and you have calculated this magnitude of the impedance. So if you have calculated that one and if you know the information of the power factor, so you can have cos of theta and sin of theta, and you can find out the from the locked rotor impedance you can find out the resistance and the reactance. And what is that resistance? Locked rotor resistance, it is the sum of the stator plus the rotor resistance, and locked rotor reactance is the sum of the stator and the rotor leakage reactances. And you have performed this test at one particular frequency, and that is the, let's suppose, the rated frequency of, in our case it will be 50 Hz. So you can find out this rotor reactance at any other frequency with the help of this expression. If you have not performed the test at the rated frequency, then you can translate it, because your reactance is the function of the frequency. By changing the frequency, the reactance will be changing. So you, if I take this expression, you have already calculated R1 with the help of the DC resistance test. So if you know R1, so you can subtract that one and you can find out R2. So using these two expressions, you can find out R1 and the R2, right? And then for any frequency, you can find out the reactance with the help of this expression, that F rated divided by F test into XLR, and that is equal to X1 plus X2, because you have calculated in combination. Okay, so now different tables are used, but over here you can see a table that is relating X1 and X2 for different types of machines. For wound rotor type machines, X1 is considered half of this XLR. For design A, 0.5 into XLR and 0.5 into XLR, X1 and X2. For B type machine, design B machines, the X1 is considered as 40% of that one and X2 is considered as 60%. For C class, 0.3, X1 is considered as 0.3 time of that one, and X2 is 0.7 or say 70% of that one. And for class D, x1 is considered as again 50% and x2 is considered as 50%. So with the help of this table you can bifurcate XLR into two parts, x1 and x2, right? So here is the data. You should try to solve this example yourself. We have the DC test data, no load test data and the Locked-rotor test data. So you are supposed to sketch the per phase equivalent circuit of this motor and you are supposed to find out some machine parameters. So that you can consider as an assignment for you. So if I summarize, we have discussed the tests which are used to determine the motor parameters: no load test, Locked-rotor test and the DC resistance test for the induction motor. With the help of that one we can determine the equivalent circuit and then we can look for the torque speed curves and we can use those ones for the design of the induction motor drives. So that's all from this video. Thank you very much.